Okay, good morning, everyone. Welcome to the Gravitational Waves Open Data Workshop number 7. And I, on the behalf of the organizing committee, welcome all of you to Taiwan and to the National Museum of Natural Science. So in the beginning, I would request Jonah Kanner to give us a few inspiring words before we initiate our Open Data Workshop.
Oh, no trouble. Good morning. You can take, yeah. Good morning. It's nice to see everyone. Welcome to the 2024 Gravitational Wave Data Open Workshop. My name is Jonah Kanner from LIGO Lab at Caltech. We are very happy that this year's workshop is being hosted by members of the Kagra collaboration for the first time in Taichung, Taiwan. In addition, this workshop is a truly global event. There are hundreds of registered participants around the world, including in-person participation at 10 study hub locations. This workshop is only possible because a large team of people contribute their time and expertise to make it happen. I want to say a special thank you to all of our mentors, to our study hub hosts, and to the organizing committee. To the participants around the world, I hope you will enjoy the workshop and that you will get a great introduction to gravitational wave science. Welcome and thank you.
Yeah. Thank you, Jonah, for your inspiring words. So before we start, I would like to have some few announcements. So we have got 2 lecture sessions in the morning, separated by a good coffee break. However, we are sorry that we are not going to provide you with lunch, so have it at your own expenses. And then if you really want us to direct to a good restaurant, please let us know. We can really take you to some or show you some good restaurants. And with that, we can begin our Open Data Workshop today. So I would request the first speaker, Takahiro Sawada-san, to present his introduction to gravitational wave science. Please. And for the online participants, you can put your questions in the chat box, and we will try to answer them as soon as possible. Thank you.
Hi, everyone. So I'm Takahiro, working at Kagra Observatory. So thanks to inviting me to and give the opportunity to share my lab for the gravitational wave, and also want to share what we are doing every day. All right, so now, fortunately, we have many of the worldwide class, that's kilometer length class of the large interferometer worldwide. So especially 2 LIGO, one in the Hanford, US, and Livingston. So that's very advanced one. And also Virgo have the 3 kilometers interferometer as well. And Kagra, so is now not operating mode. So they are working for the recovery from the damage of the earthquake that's happened so very early of this year, unfortunately. And the LIGO India, so they are now going forward. We believe they're coming a few years later, maybe they are going to the online. So now the important thing is how we can maximize the performance of the gravitational wave observatory. So that means in past it may be each observatory operating individually, but now we are cooperate together, and for example synchronizing the operation time. Then we try to maximize our global network performance to detect the gravitational wave. Then this is the photo. So maybe people cannot recognize. But so, for example, this LIGO detector, so this one of the arm have the 4 kilometer, that's very huge observatory, and another LIGO also 4 kilometer 2 arm, and Virgo 3 kilo arm. So Kagura, this is not true photo because we are implemented the detector under the mountain. So this is just a rendering, so not true photo, but so people can understand. So anyway. Okay, so this is very simplified data flow. So from the output from all the interferometer to the finally going to the public data. So that is main focus of today's workshop. So okay, so when gravitational wave across to each observatory, the interferometer output some signal, then that's immediately calibrated and reconstructed. Then the data stream, going past to the detector characterization. So that the interferometer data is very the interferometer is really complicated and controlled. So we need to know that data is really we can analyze. So that means that's have the good quality to be analyzed. So that's kind of the diagnosing and mitigating the interferometric problem. That is the role of the detector characterization. And if data is okay, that pass to this search group. So various kind of the search, targeting to the various source of the gravitational wave is running. And so when that finds some, when they identify the signal of the gravitational wave, then they will send the public alert and also starting the event validation process. That means, sometimes the data nearby the event time have some kind of the grid noise. So it could be affect the parameter estimation or something else. So that kind of things is validated by the people. Then finally, the parameter estimation again. So that's more detailed version. Then finally, when everything okay, then that's registered to the catalog. And with the manual and software and the data, etc., and going to publish by the open data group. So, but this is just very brief overview that each detail will be explained by the expert in each field. So today, tomorrow, and day after tomorrow. So I don't go into very detail, but please wait to their very expert talk. Okay, then this is what's gravitational wave. So mass tells the space-time how to curve, and space-time tells mass how to move. So Albert Einstein predict the gravitational wave existence, but that is the ripple of space-time, produced by rapidly accelerating the mass distribution. Then and that source candidate is in the LIGO-Virgo-Kagura group, categorized to the 4. So one is the coalescence of the compass source. Compass source means somehow that object have very small radii, but very high density. So such as a black hole or a neutron star, that's inspiring two of the compact stars, so inspiraling and finally merging into the two heavy objects. So that made the gravitational wave. And another candidate is a continuous wave, so rapidly rotating neutron star when that have some kind of the mountain in the surface. So that could be also emit the gravitational wave and burst asymmetric core collapse supernovae or other very moderate event. And finally, the stochastic, that is some kind of the background. And yeah, very detailed of these four categories will lecture by each expert later. So I will just move forward the gravitational wave in case of the coalescence of compact binary. That simulated figure is the right top. And yeah, this kind of the inspiring and merging making the gravitational wave, and that fly to the, for example, the Earth direction. So along with this kind of the blue tube with this kind of the motion. Then, so we are going to measure this distortion of the space-time by our detector. Okay, so go to very brief history. So Einstein predicted so GW gravitational wave in the 1960s, but finally the LIGO detector detected. That's 2015, so roughly 100 years needed because the gravitational wave effect is very, very small, and so experimental side and also theoretical side, so needed quite huge of the effort to achieve so this kind of successful. But anyway, so that was very challenging. And okay, this is still history. The 1974, so the Harris and Taylor so found the binary pulsar. So this kind of the pulsar, so along with another neutron star. So this binary system, so this pulsar timing, if pulsar is so alone, so that timing is really accurate. But so because of this kind of the binary system, so that emit the gravitational wave, and so then the plus per astron time will gradually reduce by time because of the emission energy was emission by the gravitational wave. So this observation result is very agreement with the theory prediction. So then later they get the Nobel Prize for the discovery of new type of pulsar and binary system, and the discovery of the opening the new possibility for the study of the gravitational wave. But after that, that was the indirect measurement, so people want to directly measure. So the White so proposed this kind of the basic concept using the microphone type interferometer. So that injects the laser and split into the two directions by the beam splitter 50-50, and back the beam is solely combined at the beam splitter and read out at the photodetector output. So you can see that if nothing happens, so that's this constructive at the output pole, but when gravitational wave coming and changing the both arm lengths, then the output port have the could be measured some amount of the light. So this light, so the corresponding to the motion of the arm. So then by measuring this right amount, then can be measured the distortion of the space-time. This is the basic principle of our gravitational wave interferometer. But the advanced generations one have much extra component to achieve the good sensitivity, compared to the very simplified Michelson type interferometer. But even though this cartoon still have very simplified, but anyway, so this part is similar to the Michelson, but in the more this side, so many mirrors used for the more stabilized laser, because the laser works as a ruler to measure the gravitational wave, so it should be very stable for the amplitude and phase. So that to stabilize the laser, so we have this kind of the subsystem, and also we are adding these two mirrors for making the cavity for the X arm and Y arm. So this allows us to accumulate much more laser power in this location. So then the increased amount of the laser is very helpful to measure the motion of this end mirror. So this works, improve the sensitivity in the more higher frequency region. And also many mirrors near the output port. This adjusts the output signal so that frequency dependent adjustment. Then we can optimize some frequency band to read out. Then this is we are calling as the sensitivity curve. So this shows the amount of the noise. So when gravitational wave is not coming. And then, so this data is open because now we are the observing period. So everyone can access to this kind of URLs. So for example, this is yesterday's one. So then the 2 LIGO and 1 Virgo and 1 0600, the data, you could see it. So each frequency have the different amount of the noise. So this is because so each frequency, the sensitivity is limited by the different kind of the source. So anyway, so we are fighting to reduce this kind of noise. And just very briefly, I explained some kind of the fundamental noise that's coming from the physics. So that should be minimized by the design of the interferometer. But some technical noise or environmental noise, we may be possible to reduce. So lots of time, so the worker in the on-site, so work to reduce this kind of contribution of noise. Anyway, and so now we are observing 4B, but so this is just summarization of how many events we found from 01 and 03. So that's 90 events. And so this shows the pair of the coalescing binary. Two of the objects have what kind of mass, and that's going to what kind of mass object. So this is just a representation. It's slightly changing. The x-axis is now the primary mass. This is a more heavier component. And the y-axis is the secondary mass object. So if the event is here, so that means the two of the objects have the proportional mass. And now the LK found the all combination of the binary. That means the BBH, that is the two black holes, so inspiring and finally merger, and because become the one heavier black hole, and the BNS is the merger of the two neutron star, and NSPH is the neutron star and black hole combination. Then I want to just introduce some of the milestone events. So the GW150914, that is the first direct GW detection event. And so this event, discovery, is not only the first GW detection, but also that we are showing the existence of the BBH. That's also the first time for us. So, but now this is embargo of the detected source. That means we have much more events already founded. And okay, this event is very milestone for us, not only for the LBK people, also for the astronomy. So the down of the gravitational astrophysics event. So that's okay. And finally, the three people much contributed in the early stage of the construction of LIGO and develop it. So congratulations. And okay, later, so the teacher introduced us, but so very briefly explain what kind of the information we can obtain from the data. So this is the waveform. The x-axis is times, and the y-axis is the strain. And so this, so this kind of the shape is coming from the gravitational wave. So from this waveform, we could know how massive were the two black holes, and also how much were they spinning, how far apart they before the touch, and how massive is the final black hole, etc., etc. That's kind of thing we can extract from this waveform. So, okay, anyway. Anyway, yeah. So actually, so gravitational wave just distorted our space-time, so we couldn't hear by our eye, ear, but so this frequency is somehow similar to the kind of the sound, so we can convert to the sound in this movie. And anyway, then the next important event is the GW70817. So this is first BNS merger. But not only we are detecting this kind of one, so this is important meaning as the birth of multi-messenger astronomy with GWs. Okay, anyway. Okay, now, this video is a simulation of the two of the neutron stars inspiring and merging, and finally emit many other things. So this kind of the emitted object allow us, I'm sorry. So allow us to measure the many other than the gravitational wave. So for example, this shows this is the signal of the gravitational wave observed in the LIGO. But after that, several seconds later, so the GRB also the gamma ray is observed by the another so detector. And not only that, so many of the observatory on the Earth and also the space. So finally, the 70 group using the 100 instrument, so looked at the remnant from the BNS merger. So this represents about 1/4 of the world's astronomers. So then this is some summary of the various kind of the observatories so found when from the merger time. So first, so GW is so here, and just after that, so gamma ray observed, and X-ray and UV optical IR radio also observed after that. So that's okay. Then there are many things we learn from this event. For example, the gamma ray and gravitational waves so arrived to very similar timing. That means the gravitational wave travel at the very close to the speed of light. And also the neutron star collision can make gamma ray burst. And also the localizing this event, so many astronomers can observe them with different telescopes. Then we could learn many of the information we call as the multi-messenger astronomy. And from those results show the significant signature of the heavy element like gold and platinum is generated after that. So many of things we could learn from this. So exploiting the multiple messenger information, so that because the GW detection that released energy by the BNS is not only for the GW. So other type of the radiation also could be emitted. So this time, if that's confirmed, like electromagnetic or neutrino or white star, that's possibly. So what LVK is doing is so some astrophysical alert is there provided by the other partner or any other experiment. Then we are doing some targeting search that try to find the GW signature and try to find some coincident time and location, for example. And vice versa, when LVK found some signature of the GW, we are sending the alert to the astronomer. And they can also do this vice versa thing. That means they are also try to find some correlation between the GW and their experimental result. So in O2, that kind of agreement signed with the 75 group, 150 instrument, and 10 space observatory. But from O3, we are more sending the public alert as soon as possible through the GCN. And O4 with also some change. So I will explain later. Okay, and briefly explain another interesting event so far is the one is some VH existing the pair instability mass gaps that have the very higher mass, and the next one is the compact object heavier than neutron star but lighter than the V8 also exists. The third one is binary system with have large mass ratio. That means one of the mass is very high, but one of the mass is very low or something like that. That's kind of asymmetric mass ratio. And the final one is the first NSVH merger. One object is neutron star, and another one is black hole. That's also found to make the merger. but not only such a detection, so now we have variety of other results because, so now we are not only have some individual one, so we have already have enough amount of the statistics now. So we can start to say many of the some population or merger rate or some related. So physics, you're using such a enough number of statistics. And also the test of general relativity and cosmology, like a Hubble constant determination, or upper limit for the vast continuous wave stochastic background signal, also reported and summarized in this paper, GWTC. So people can read, so not only, so we have published each detection paper, so we also have this summary paper now, so people can read it. And so I am very happy to announce this one. So LVK, so really announced discovery of the new type of the event in this early April. So this is the merger of the one object, the 1.4 solar mass. This is certainly the neutron, but another one is 3.6 solar mass. This is truly the gap we are calling as the mass gap. So that is larger than the expected range for the neutron star, but smaller than the expected range for the black hole. So now we are understanding, so now we made no gap in this kind of map. But anyway, so this paper is published, submitted to early this April, and this is the first paper from the O4A observation period. Okay, so let me explain the current and ongoing observing run O4B. So from April 10th, so just 1 week before from today, so we have started the O4B observation. So now 3 detectors, 2 LIGO and 1 Virgo detector is joining to the observation, while the Kagura are planning to join the very late stage of the O4B. But anyway, so you can see the latest announcement on this URL. So this is frequently updated, usually so every 1 month. But anyway. And after that kind of picture, sometimes people ask me why you are alternating data taking and the update period. So I want to answer it now. So, okay, so this is some kind of the simulation. If we are just going to the observation, so without taking the upgrade period, so if we are continue to the observation with the O3 performance or detector, so the number of detection is increasing this kind of way. But if we are taking the 1 month or the upgrade period and increasing the sensitivity, and so after 1 year, so we could get much more event than the no upgrade, even though the observing period become much shorter. And the same thing, so if we are taking some upgrade, so repeatedly and continue to increase our sensitivity, so finally, so we could get much more event in the final. So that is the reason, so we are continue to alternating the data taking period and upgrade period. Anyway, so this is the number of events. So how many events is observed so far? And you could see compared to the O1 and O2, So from start of the O3, we are immediately drastically increase the detection rate. The horizontal axis is the accumulate time of the observation, and the y-axis is the cumulative detection number. So from O3, the detection rate drastically increased, so that's coming from the increasement of the detector performance. And O4, it might be so difficult to see by eye, but so you could see that from O3 to O4 also, so the detection rate is much higher. And not only the detection rate increasement, so we also improve the public alert, that latency decrease, and the localization and classification also we are improving in the O4A and O4B. And now we are just starting the O4B, and we already found the first event from the O4B. So we are waiting so much more interesting event coming from the O4B soon. Okay, so this is just our first alert, significant detection alert from the O4B. So congratulations in April 13. But anyway, so we have started to detect the gravitational wave candidate from O4B now. So all this kind of alert will release publicity short time after we detected. Okay, then I just want to explain the difference of the public alert in O4, so compared to the O3. You can see the detail in this homepage, but so the large difference we have, two differences. The first one is in O4, we are sending the two types of the public alert based on the false alarm rate. So in O4, we are categorize the alert is two. So one is the significant alert, and another one is the low significance alert. So this is, we are categorized by the false alarm rate value. And so this significant alert is so corresponding to the previous alert used in the O3. But now the people can also see the low significant alert. This is the false alarm rate is not so good. But so if people have the interested, so you can see it. So we are so open, so such alert also in the O4. And also another interesting thing is the new early warning alert stream. So this is aimed to send the alert before so merger happen in case of the BNS. So we are calling as the negative latency alert, so up to 10 of the second from the merger. And so we are also describe some public alert sequence, this slightly updated from the O3. Okay, in final, so we want to introduce the Open MMA forum. So this former is we are calling as the Open LVKEM. But anyway, so this forum is aimed to the exchange of the information to the multi-messenger astrophysics people. So, and this page have the many of various useful links of the LVK document and the resource, and also the link to the telecom and the app, etc. So just I want to advertise, and the people, if people want to register, that's very happy. Okay, and this is a summary. So from O1 to O3, so LVK confirmed the 90 so confidence detection candidate, and many of the harvests of the scientific results obtained. And we are started to show the result of the O4A, and also now we are just now, 1 week ago, we started the O4B observing run, and that's 3 detectors at beginning. So we are crossing fingers to see many more interesting events to be discovered. Okay, thank you.
Okay, thank you, Sawada-san, for the interesting talk. So it's time for question and answer. So any questions from the on-site people? Any questions? Okay.
Is there any three black holes collision together, or only two?
So our detected event, so we don't have these three so black hole merger. We don't yet have such a discovery yet. But maybe if your question is that kind of the event could be possible for the theoretical calculation or something, maybe I can pass some theorists in this on site. Maybe how about the Shinkai-san? Maybe you can provide much more better answer than me.
Well, generally speaking, three-body collision might be quite rare. So if you are too lucky to detect it, if it exists. But before that, we need to have a theoretical prediction of the waveform because normally gravitational wave data is quite noisy. So maybe in the future, you can play with that, I hope.
Okay, so any more questions on site? Do you have questions online? Online participants can put your questions in the QA box, and then we can address them. In the meantime, I have a naive question to Sawada-san. So, as we know that there can be some people online and on-site for whom gravitational wave observations or data analysis could be for the first time they are attending. So I was wondering if you could suggest something from where they can start their studies on GWs, both from the viewpoint of theory and observation. Yeah, so I was thinking if you can suggest some like a very basic starting point for gravitational wave observation, both in the domain of theory and data analysis, to the newcomer or the beginners.
So this lecture continues to be that's the start for you.
That's very good. So do we still have any online questions? Okay. Yeah, there's an online question. Let me read it out. Would you expect an increase in search of EM counterpart in this new cycle?
In search of EM counterpart mean the sorry.
So we've only had a small number of BNS detections. We've had a very small number of electromagnetic counterparts. That would be one. So I would understand the question as, in the new run coming up in O4B, do we expect a higher rate of binary neutron star detections? Do we expect a higher rate of electromagnetic counterparts? Does that question make sense?
Okay, so yeah. So if you could just enlighten this answer.
What rate of electromagnetic counterparts do you expect for O4b?
The exact number.
In my personal understanding, there are several literatures try to estimate the EM counterpart of the possible detection of in the O4b. There are some optimistic estimation and some, but at least we propose the OVO for 1.5 years. It means that originally, we suppose that we can at least observe one more binary neutron star merger detection during the O4. Although we don't know whether it is true, but it might be before the past experience and the theoretical estimation. Yeah, I read some information from the paper. Yeah, but if we are lucky enough, maybe we can observe more events. But unfortunately, it seems in the overall we did not detect another binary neutron star merger event. So we cannot use it to trace the another EM counterpart.
Okay, so probably okay, that's another question.
I have no idea about the time scale of the event. So our purpose of this public alert is mainly on appointing that source for EM counterpart or something like that. So I just want to know what is the fastest EM counterpart we are going to observe, or any other EM counterpart, maybe in terms of time scale, So and how fast we can detect the EM counterpart in our systems, or
Okay, so let me go for. So your question is how fast we can send the alert for the BNS detection? Is that true?
Events. Just I don't have any impression about the time scale. So maybe you have some ideas.
Okay, so I'm sorry. Oh, I'm sorry. So in our expectation, so in O4, as I say, so we are starting the early warning. So that's we are so speed up the infrastructure and also the pipeline. So some pipeline can send the alert before starting the merger. So that fully automated system. So our expectation is before 10 seconds or something before the merger. That is our expectation. Of course, that depends on the distance or mass or something, but in the average, we expect that kind of time scale.
Okay. Yeah.
Yeah, maybe is it okay if I try to add to that?
Mm-hmm.
Yeah. So as he says, right, the analysis is quite fast. So we're able to get out alerts on timescales of seconds or minutes. In the best case scenario, it might even be possible to get out an alert before the merger. So that's a bit of a frontier work, but maybe possible. But in general, seconds to minutes to get the analysis out and to get the alert out. In terms of the electromagnetic counterparts, it's all timescales. And so, there's, for the case of 170817, which is the one observational case we have, right, there was a gamma ray burst that happened 2 seconds after the merger, so very fast, seconds. There can be, in general, the higher energies seem to have faster timescales than lower energies. So an X-ray counterpart or an ultraviolet counterpart might last for perhaps hours, let's say. And then the optical counterpart, we know, lasts for days, up to a couple of weeks. And then the radio counterpart actually was visible months later. And of course, that's for one particular class of signal, for the kilonova signal. In principle, you could imagine maybe in the future we'll find other things as well. So the timescales, it's many different timescales. But in general, we're targeting to have the information out within, say, seconds to minutes so that astronomers can respond promptly and catch the prompt, the more prompt emission. Yeah. And of course, as with many things in transient astronomy, if you can catch it in the early phases, either while it's still brightening or while it's very bright, then makes it, you can get the most information out, right? And then so the brightening is generally very fast, and then like many transients, the brightening is fast, and then the dimming is long. So there's a big advantage to getting the information out very fast.
That's great. Thanks, Jonah, for the answer. Do you have any more questions online? No, not yet. Okay, so there are no more questions. So any more questions that any on-site participants would like to ask? We still have some time. Maybe we just give you a couple of moments to think. Okay, yeah, please go ahead.
Okay, so I have one question related to the first question asked. Because currently we are doing the model search. If we do not build up the template for the three-body black hole merger, how do we find it, right? So maybe we'll have to build the template first in order to detect those kinds of events. Is that correct?
Okay, so we have such a kind of we are called as the model search using the template. So, but not only that, we also have many of the pipeline with unmodeled search that try to find some kind of the enhancement of the signal and see the coincidence between the detector, for example. So that's kind of one, if, okay, the three capacitor merger happen and make the significant level of the signal, so that could be measured, detected by such kind of the unmodeled search. Yeah.
Okay, thank you very much.
Okay, so any more questions? On-site people, okay.
Yeah, just a very fast follow-up after the question. So after detections, I think what we want the most is to confirm what kind of event it is. But without waveforms, how could we confirm like it's a three body or something else?
I think, Andy, could you repeat your question one more time?
Yeah, if we do not have templates, how can we confirm it's either a three-body coalescence or some other transients?
Okay.
Okay, information provided in the public, so that depends on for which pipeline find the event. For example, if the CBC and template search find the event and the parameter estimation is completed, so that also provides some kind of the information we call as a peer store. This probability of the source is coming from the BBH is 98% or something like that. But a model search case, maybe, I I should double check, but so that's kind of the, what is the source? Maybe not included in. So that only found the some kind of the, this kind of direction and some confidence level or something like that. It might be because the, I don't think there is such kind of the three compact object merger could be, so, classified from our template or something. So maybe if that happen, may not write this coming from these three body, but maybe alert could be sent with some kind of information.
May I comment on that? So actually, the question you are asking is related to the lectures in day 3 about the parameter estimations. Right? So if we have a detection, the unmodeled pipeline will telling us, okay, we find some events there, but what are those events? We will do further detailed parameter estimations. So currently we focus on the binary compact merger, but if the event we detected is not so alike to the binary CBC events, then yeah, we will have a further investigation on what kind of events we are detecting, right? Yeah.
So let me make some advertisement. So if you want to know how to run the mesh filtering and how to do the parameter estimation, and maybe I will use the AI to check the component mass of the gravitational wave event, you should follow our lectures later.
Thank you, Lupin, for the advertisement.
There's one online question.
Okay.
By 3 objects, it means pure 3-body problem or one binary system orbiting another object. Well, so the motion of the three masses is really complicated, right? Yeah. So the motion of 2 compact bodies, we can describe them on one 2D plane, but for the 3 body, it's really hard to describe their motions, right?
Yeah, so how would you like to respond to that question? I think the question is about about the 3-body problem. Let me read it out again.
Yeah, the question is, the 3 object means that's a 3-body problems, or it's another compact object orbiting on a binary system?
To me, or
Yeah,
No, that's the question.
that's the question online. People.
yeah. So I don't know. I never made the 3 objects yet. So, but yeah.
So many simulations show that each body might not exist so long time. So maybe we should consider binary plus one single star, like a limited 3-body problem.
Okay, I hope that answers the question. I guess we have another question online. Okay, so the number is that why the number of detected BNS mergers is so small compared to the detected BBH mergers? Let me repeat the question for the on-site participants. Why the number of detected BNS mergers is so small compared to the detected binary black hole mergers?
Yeah, that's a very good question. Yeah, because I heard, yeah, because I didn't join the advocate so long before, but I heard some stories, so we are expecting the BNS merger much more than the, yeah, before starting the observation, we have people expecting much more BNS rather than the BB8, but actually, so this is the result. So that's the thing we also want to know. So what the reason of this kind of the ratio of the BNS and BB8, it might be coming from some kind of the evolution or the universe or whatever. So, but I still don't know the exact answer now. So that is the reason also we couldn't say the accurate expected number of the BNS in the coming ongoing the observation, for example. But anyway, I'm sorry to.
Okay, I guess we're at the hour. Okay, so we can have a coffee break for half an hour, and then we come back at 11 to resume the open data workshop. Thank you everyone for participating. And let's thank the speaker for the session, Sawada-san, for his wonderful lecture and interesting pointing out things.